Hey, we are back to start with alpha decay. So it's our first type of radioactive decay we're going to cover. An alpha particle is the same as writing it as 4,2 helium or 4,2 alpha. So what that means is that it's got an atomic mass of 4 and an atomic number of 2. That's why we can interchange the helium with the alpha. So when the nucleus breaks down, it's going to release a particle that has 2 protons and 2 neutrons, giving us the atomic mass of 4. And because it's got 2 protons, that means it is a helium atom, but at the same time, because it came from a nucleus, it's an alpha particle. So it's not a little bit different, but similar, right? There's not going to be any electrons around it, whereas a true helium would be 2 electrons as well. This is one of the most common modes of decay, especially for heavy nuclei. So uranium and radon will both do these types of decay. And in fact, we've got some examples here. So uranium-238, which is just a type of uranium, an isotope of uranium. So it's atomic mass 238, atomic number 92. When it releases an alpha particle, your atomic number goes down by 2. So this is where you always want to start checking on the periodic table. You're going to say, I've got uranium. I know it's going to release 2 protons, so that means it's going to go from 92 to 90. Then I would check on my handy-dandy periodic table, find element number 90, happens to be thorium. Now, you can't just take thorium's atomic mass, because on the periodic table, if you look, it says 230, where am I? 2 other way, there it is. 232, but notice here it says 234. That's because, again, we're talking about isotopes. So you have to conserve that mass, which means if we know I started with 238, I released 4 mass units, I'm going to end up with 234, not the 232 that it says on the periodic table. So you always have to start with what you're given and subtract that particle that's being produced. There is a practice problem for alpha decay posted in Google Classroom, so make sure that you do that after this lecture. The next type of decay is beta particle or beta decay. Another very common mode of decay. It has no mass. How is that possible, you ask? Well, let me tell you. It is used when you have unstable elements that have too many neutrons. And this neutron will decay into a proton. So the neutron is going to change from no charge to a particle that has a charge, specifically a proton, so a positive charge. The way that it does that is by involving particles that are even smaller than our protons, neutrons, and electrons. We call them quarks. It's not something we're going to do in general chemistry. You won't do it in your first semester of Gen Chem in college, and you might not do it in your second semester. Personally, when I went to Iowa State, they did it in physics. They didn't even put it in chemistry, so that's where physics and chemistry overlap. Weird things happen when they do that. But anyway, what you need to know is that a neutron becomes a proton. So since we have a neutron that is becoming a proton, it's like adding 1. So in this example, we start with element 88, and we're going to move up to element 89. And because it has no atomic mass, then the atomic mass stays the same. You write beta in this funny looking B, so it's like a B with a kind of extra long tail. It goes up and around. And then you're going to put a 0 for the atomic mass and a -1 for the atomic number, because that neutron becomes a proton. There is an example for you to do, again, on Google Classroom, so take a look at that. Gamma decay is what accompanies other types of decay. So gamma radiation, you might always think of the Hulk. That's kind of the first thing that comes to my mind. But what happens is that gamma ray or gamma decay is a high energy photon of light. So photons are what are the packets that light is made up of. And when things decay, sometimes they release energy in the form of light. And that's the gamma ray. So it accompanies, like I said, other decay processes. It has no charge, no mass number, and no atomic number. So you write it like this, the 0, 0, and then it's like a V with a thing over it. So in this case, it's accompanying our beta decay because we go from carbon 6 to nitrogen, which is 7. Notice that the atomic mass stays 14 and 14. So we know it's a beta decay, so 0, -1 E, or the 0, -1 in that funny B you can write. And this is the gamma ray. And it's just a way for a nucleus to release excess energy, and it just happens to be in the form of light. Positron decay, oopsies, there we go. Positron decay is going to be different than beta decay. You notice that beta decay had the -1 here. Positron is going to be a +1. So it's a particle that has the same mass but the opposite charge of an electron. So essentially electrons have no mass, and because an electron is negative, then the opposite of that is going to be positive. So it's 0 and then a +1 E. Positron is basically the opposite of beta decay. It has the effect of changing a proton into a neutron. So when we look at our example with magnesium, magnesium's atomic number is 12. When it undergoes positron decay, one of the neutrons is going to be changed into a proton. So it goes, I said that wrong. One of the protons is going to be changed into a neutron, excuse me. So it goes from 12 to 11, which is sodium, because one of these protons changed into a neutron. But because it's a straight exchange, your atomic mass doesn't change. So 23 and 23 stays the same at the top. And then you have your positron symbol plus a gamma ray, because there's a lot of energy that's being released there. If you guys don't include the gamma ray in your equations, it's totally fine with me. I just want you to be aware that that gamma ray often comes off of other types of nuclear decay. Here is manganese, so 25, undergoing positron decay. So one of these protons becomes a neutron forming element 24, atomic mass 50 and 50, and again, that symbol indicating positron. The last one we're going to talk about is electron capture. And so you know you have your valence electrons and your core electrons. The core ones are really close to the nucleus, and sometimes those can fall into the nucleus. And so that's when one of these inner electrons is captured by the nucleus. It doesn't happen very often, but because it is such a massive amount of energy that's being involved, it will always be accompanied by a gamma ray, and it will decrease the number of protons. So the symbol is very similar to the beta decay, so 0, -1 E. However, this is going to be part of the reactant side, not part of the products, because your nucleus is capturing this electron to make something new. In beta decay, we were releasing that beta particle. In electron capture, it's falling into the nucleus and it's part of the reactants, not the products. That's the main difference here. So notice that we've got element 27 capturing an electron to become element 26, but our atomic mass stays the same. So this is just a bunch of different examples here. The last slide I want to talk about is this table. Oh dear, we can't see it all. You can't see the whole thing. I apologize for that. I will maybe move it up, see if that helps at all. Nope. Here we go. I know how to use a computer, I swear. All right. So I recommend jotting this down so that you can more easily do those practice problems on Google Classroom. You can see that I've just taken our table, or our types of decay, and put them into a quick table for you. So alpha decay has the 2,4 helium, or the 2,4 alpha, as its symbol. It will increase the mass number by, decrease the mass number by 4 and decrease the atomic number by 2. Beta decay is 0, -1 E, or that beta symbol. It has no change to the mass number, and you increase the atomic number, but remember, beta decay is on the product side. Positron 0 + 1 E, again no change in mass number, decreasing atomic number by 1. electron capture 0, -1 e, no change in mass, decrease atomic number by 1, and again, this one is going to be on the reactant side, so make sure that you have it on the reactant side, not the product side. Gamma ray, 0, 0 gamma, no change, no change. So please try and complete those problems on Google Classroom.